you are keenly interested in knowing how radar technology can help you as air traffic control specialists locate and warn pilots of such meteorological problems as thunderstorm gust fronts, strong shifting winds both at the surface and aloft, severe storms of all kinds, especially damaging winds, tornadoes, and hailstones. You're about to see a demonstration of Doppler radar, which has evolved into NEXRAD, an acronym meaning Next Generation Weather Radar. NEXRAD is primarily designed and built around the Doppler radar system. The National Severe Storms Laboratory, a part of the National Oceanic and Atmospheric Administration, NOAA, in Norman, Oklahoma, is a prime focal point for Doppler radar research in the United States. Cooperating in the research activities with NOAA are the Federal Aviation Administration and the Air Force Air Weather Service. Before proceeding, let's briefly cover the makeup of a thunderstorm. In any developing thunderstorm, warm air is drawn in from lower levels and is forced aloft, thus cooling the air, forming clouds and precipitation. Downdrafts are caused by frictional drag of the precipitation, creating a cool outflow of air from a thunderstorm, the leading edge of which is a gust front. This is a classical severe thunderstorm. First of all, notice that you're viewing this picture from the east looking west. The upper winds are from the southwest to the northeast. The anvil streams off to the northeast. Precipitation is occurring in the northern portions of the thunderstorm. Airflow at lower levels, usually from the south, is forced upward and aloft into the thunderstorm. As the air moves into the thunderstorm, it can develop a spiraling motion, much like the water draining out of a bathtub. This spiraling motion produces the mesocyclone, a small rotating circulation less than 10 miles in diameter. The wall cloud and tornado are an outgrowth of this rotation. You can see the rotation in this film. Notice that the tornado occurs to the south of the precipitation in the precipitation-free base area where maximum inflow occurs. Hail often occurs just to the east and north of the wall cloud. Here we have a schematic of a thunderstorm with a Doppler radar beam passing through it. The beam is narrow, less than 1 degree. Therefore, as it scans horizontally, the radar will only analyze that portion of the thunderstorm the beam passes through. To arrive at a picture of what is happening at different elevations of a thunderstorm, the antenna tilt is varied. Thus, it is possible to observe varying patterns that occur at different altitudes. Precipitation droplets act as radar targets. Law enforcement radar utilizes the Doppler principle, measuring the velocity of targets as they move toward or away from the antenna. Much like the law enforcement radar, Doppler weather radar can detect, measure, and display these precipitation targets as they move toward and away from the antenna. As shown here, the gust front marks the leading edge of the outflow of cold air and usually lies ahead of precipitation targets. Even though no precipitation exists, the Doppler's radar beam is refracted and returned by the gust front's sharp temperature and moisture gradients and by dust and debris. The Doppler can analyze gust front velocities in detail out to 35 miles and in less detail out to about 70 miles. What you're about to see here in the research laboratory is not necessarily what you'll have in your facility in the future. Our purpose is to acquaint you with some of the capabilities of Doppler radar. Note in our demonstration that Doppler has several different scopes that must be monitored simultaneously to get the composite total picture of the storm. Each of the Doppler scopes displays a certain parameter which is very important to the total picture. The first Doppler scope is the reflectivity display. This is much like the conventional radar displays, except that the colors showing the intensity levels are different to that which you're accustomed to seeing. The second scope is the velocity display, which is new to you and shows the radial velocity within and near the storm. That is, it measures the velocity coming toward and going away from the radar by showing them in contrasting colors with the speed shown on the color scale at the right side of the display. Next is the spectrum width or the spectrum spreading display. This display is of particular interest to air traffic specialists because it helps pinpoint areas of turbulence and measures their intensity. Velocity spectrum width is the variance of radial wind speed within the radar beam. The greater the difference, the more severe the shear and turbulence. As verified by aircraft penetration, values of greater than 4 meters per second indicate possible significant turbulence. As you view this presentation, keep in mind which scope is being shown. The colors on each display, selected by research meteorologists, are designed to enhance the dangerous parts of the storm. Don Burgess, Gene Lee, and Dick Doviak, research personnel at the National Severe Storms Lab, will explain what can be obtained from each scope display. First will be Don Burgess.
The Doppler radar and these color displays are really a new innovation and a great addition in our abilities to work with severe storms. Previously, as you know, we had the black and white display with shades of gray. And if we had a tornadic thunderstorm, such as the one right here I'm pointing to, it was sometimes difficult to determine if you had this feature we call a hook echo, or a figure 6 that was related to circulation. With Doppler radar, we don't have to rely upon this signature any longer. And I'd like to show you a case study from a storm on the 30th of April, 1978, where with our Doppler radar we were able to detect a tornado as it formed in the clouds, touch down, and begin to inflict damage. This is the color display for reflectivity on that day, and it's much like a standard PPI scope of radar as you're familiar with it. And we have a distribution of echo, several echoes to the northwest and to the north and to the northeast of the radar here in Norman at the center. We have range marks in white that are at 100-kilometer intervals. These are about 50 miles apart, and so we're looking out over most of the state of Oklahoma, some of Texas, and a little bit of Kansas. We're going to focus in here on one particular storm, this one just northwest of the radar. We'll look at the cursor and find that that storm is about 330 degrees at 50 kilometers away from us. We're going to expand the display and just have one storm fill the screen. Now this is possible with our system because it is an interactive terminal. We can position the cursor, we can change the amount of data we show, the size of an echo, and we have a lot of control about the data that's displayed. Right now we'll go ahead and have this thing update. We're just going to show the one echo that has the severe storm characteristics. When we look at that storm in the reflectivity field here, we see an average sized thunderstorm, and it has a fairly strong core, strong enough to indicate the possibility of hail. We do not know whether or not there is a tornado present by looking at this display. The advantage of Doppler is being able to look at the velocity information and get a better handle on what's going on in the wind field inside this thunderstorm. So next we'll look at the velocity data. The increasingly bright green colors are stronger flow toward the radar. The increasingly bright red colors are stronger and stronger flow away from the radar. If we have a mesocyclone, if we have a vortex such as that about a tornado, we would expect green on one side of the vortex, flow toward the radar, red on the other side, the flow away from the radar. And that's exactly what we see beginning to take place right at this location. We're now looking at an elevation angle up inside the storm, and this tape is being replayed just as the data was coming in real time. Now we'll get a look at what's happening down on the ground, and we find that this same signature is now extending down toward the surface. That is, the tornado is forming inside the cloud. Doppler radar is picking up its signature, the change in color from bright green to bright red, showing the exact location of that tornado. We can take our cursor, focus in on it, get an azimuth and a range that give us an accurate position of that tornado to within less than 1 kilometer in space, and very precise warning information is available from this radar system. As the data will update, as we see other elevation angles within the storm, we'll find that this feature has continuity with height and time. This is our signature for a tornado. It's a much easier signature to see than the old one of the Hook Echo, and it's much more reliable, and we get quantitative information in that we have very bright green, that is very strong flow toward the radar, adjacent to very bright red, the very strong flow away from the radar. We're now looking at another Doppler velocity display during the time period of the tornado, the signature right here. The display is going to update in a few seconds. Right now, when it does, you'll see that this same signature is appearing even though we've changed elevation angles. An advantage of the Doppler radar is that the circulation has continuity with height. We get this signature no matter where we're looking within the storm. It's easier to use than the Hook Echo, and the information is more quantitative. If you look here at the velocities, they give you some idea as to the intensity of the circulation, and in this case, they give you the information that lets you know a tornado is occurring in this storm. And if we look over at the width display, at the same time, we see very large values of width, the red color here, indicating a lot of shear and turbulence, perhaps some eddies right in and around that tornado. And the Doppler width then gives us a signature for the tornado as well. There are other uses for the width, such as gust fronts and turbulence work where there are no tornadoes. Gene Lee will cover those.
Part of our program here has been to look into the use of Doppler radar as it pertains to the safety of flight through thunderstorm and thunderstorm areas. In previous years, we've been penetrating these thunderstorms through the use of fighter-type aircraft like the F-4 Phantom and the F-106 aircraft furnished by the NASA and by the Air Force. And as these aircraft penetrate the thunderstorms, we observe their flight path with the Doppler radar. Now on regular radar, you can see the precipitation particles, and so you can tell where the rain is along the precipitation flight path. However, the relationship between rain and turbulence and other weather hazards is not clearly defined. Through the use of Doppler, we can begin to see where the turbulent areas are in these thunderstorms and in the areas around the thunderstorms. With respect to the reflectivity, we see where the heavy precipitation is, but the relationship between the precipitation and the turbulence in that is something that is not a unique situation. When we shift to spectrum width, we're looking at how the air is moving within that pulse volume. Now, if all the air is moving at the same speed, we're going to have an estimate of the velocity which will roughly be the same, so that we'll have a very narrow width. That is, almost all values will read the same speed. As these area becomes more turbulent in the pulse volume, we'll get quite a variation in the speed, and therefore we'll get a broader spectrum width. And therefore we equate this broad spectrum width with the turbulence. And as we flew the aircraft through these storms, we did find that as we went through these large areas of the yellows, the blues and the yellows and the reds, that the aircraft experienced moderate to severe turbulence. In fact, on this particular day, on the 16th of June, this 1980, the aircraft pilot reported that it was so turbulent that it was very hard for him even to reach to the toggle switches to turn the data on and off as we made these penetrations. Through getting this type of data, we have been able to determine that there has been a fairly good correlation between the spectrum width and the turbulence which the aircraft experience. Now, in addition to the turbulence which is in thunderstorms and which now, of course, most aircraft should avoid anyway, the most important thing, as was mentioned earlier, is the thunderstorm gust front. Now, the Doppler radar can see gust fronts, and this will be shown next by Dr. Doviak.
As Gene Lee mentioned, probably one of the most hazardous thunderstorm phenomena is the gust front. What I'd like to show you now is a gust front as seen by the Doppler radar. Before I show you the velocity display, I'd like to call your attention to the reflectivity display. Here we have a thunderstorm region in which there is very heavy rainfall. Out in front of that thunderstorm, we notice this thin line. This thin line is the, if you like, radar reflectivity depiction of a gust front. To realize that this is a gust front, we must refer ourselves to the velocity display. Here we see that same thin line in the velocity display. However, we do notice that the thin line shows velocities in the green. Green showing velocities toward the radar. Speeds up to minus 11 meters per second, or about 22 knots. So this is air moving away from the thunderstorm, which is back here, toward the radar. This air does not contain precipitation. However, there are targets being kicked up by the strong outflow of the thunderstorm, dust, debris, and so forth, which are sensed by the radar. And those targets do provide us the measure of wind speed in the clear air. And this is particularly hazardous to the aircraft because there is no visible, if you like, precipitation that the aircraft can see to avoid the thunderstorm. So these are, if you like, invisible wind shift lines. The air in front of the gust front is moving toward the thunderstorm, feeding warm air into the thunderstorm. This is a low-level phenomena. It's very close to the surface of the Earth. It has a height maybe no more than 200, 300, 400 meters. And the aircraft which are landing at airports, of course, have difficulty in negotiating landings when there is a strong wind shift in the path.
The next presentation is the Fort Sill thunderstorm. It illustrates severe turbulence in an area of light precipitation. You'll see the importance of having all three scope displays. First, the reflectivity scope. The highest decibel reflectivity is 65, which indicates a severe thunderstorm. Next, the velocity display. Strongest winds away from the antenna are 32 meters per second, or 64 knots at about 6,500 feet. Note that the strongest velocity is to the southeast of the heavy precipitation. This indicates a strong turbulent outflow of air to the southeast of the thunderstorm. Finally, the spectrum width display of the same storm. The highest spectrum width is almost 11 meters per second, deep into the danger zone. Note this danger area is well to the southeast of the heaviest precipitation and actually is in an area of light precipitation. This indicates considerable turbulence caused by the strong interaction between warm air flowing into the thunderstorm and cold air moving out of the thunderstorm. Should a pilot using airborne radar circumnavigate the strong echo by passing the thunderstorm to the southeast, severe turbulence would be encountered. Now let's discuss the possibilities of remoting this information to the field stations. To illustrate this, let's look at a plan position indicator WSR 57 radar. This is the data that is actually portrayed on the radar screen. How might this be remoted into the station? Well, one example might be this display. The boxes indicate a forecast of thunderstorm movement during the next hour. This type of remote display could be very useful to the air traffic specialists. Of course, the Doppler probably will not be remoted in this fashion, but this does indicate that the data can be displayed in various ways to meet the user's needs. From the comments by Dr. Doviak and Mr. Burgess, you realize that Doppler technology is complex. Yet you can see how it can simplify our task in locating strong winds and turbulence. Gene Lee has shown us that we need to monitor areas of heavy rain, areas containing strong winds, especially near the ground, and turbulent boundaries that advance with storm outflow. Now researchers must discover efficient methods to process and composite these areas to build simplified displays for use at FAA facilities. The National Weather Service is forming a techniques development branch at NSSL to address a wide variety of user requirements. And NSSL hopes to have computer software developed within the next 3 years, while industry is designing and producing the first basic radar systems. Doppler radar, a research tool that may become the next generation weather radar for use in terminal and en route areas for aviation weather advisories.